SwayamPrabha. Digital India. Educated India.
cube at x equal to L equal to 0. Okay, you can see that moment mxx was equal to del 2 w del x square or proportional to it or some constants, and shear force was dmxx by dx. Okay, so therefore this is the free end condition. Here's the free end condition. Okay, now if we substitute this here, you see u3 is 0, du3 is 0. Okay, so out of these, this anyway is 0, this anyway is 0, this anyway is 0, this anyway is 0, this is 0, and this is 0. Okay, so now what we get is, okay, and here also this is 0, this is 0. Okay, and if I set u3 at x equal to 0, you can see that this c term is 0 anyway and d term is 0. That's what we said over here. At x equal to 0, b, c, d are 0. So this kind of becomes an identity and gets eliminated completely. Okay, similarly, if you look at this here, this at x equal to 0 is 0, we are saying. Okay, and then at x equal to 0, b is 0 and c is 0. So this also becomes an identity. Okay, now what we are left with is here d3 u3 dx square, okay, at x equal to L. Okay, so if I make this x equal to L, okay, then what do I have? This term is 0 by the boundary condition, this term is 0 by the boundary condition, this gets evaluated at lambda L, this gets evaluated at lambda L. Okay, so what does this equation give me now? At x equal to L, d3 u3 dx square is 0 by this boundary condition. Okay, so I have a 0 that is equal to d2 u3 dx square 0 into a lambda L plus 1 by lambda d3 u3 dx cube 0 b lambda L. Similarly, what does this say? At x equal to L, d3 u3 dx cube is also 0. This is 0 from the boundary condition. We are again left with d evaluated at lambda L and a evaluated at lambda L. So that gives me 0 equal to d lambda into d2 u3 dx square of 0 into d of lambda L plus d3 u3 0 by dx cube into a lambda L. These are the two equations that are left. So if we now put it in a matrix form, I put it in a matrix form, A of lambda L 1 over lambda B of lambda L lambda D of lambda L, then A of lambda L into d2 u3 dx square 0 and d3 u3 dx cube 0 equal to 0. Okay. You can also see that this was the boundary condition for rotation delta beta. This is the boundary condition for delta beta. This is the moment and this is the boundary condition for delta beta, whereas this is the shear force and this goes with delta W. So at x equal to 0, what did we do? At x equal to 0, we specified W 0, displacement 0, and we specified W dash 0. So we specified the beta, we specified the W, and therefore these remain unknowns. Okay, and they cannot be 0. So now for non-trivial values of these two terms, the only way the right side can be 0 is if the determinant of this goes to 0. Determinant of this matrix goes to 0. Okay. So the determinant looks like what? Determinant now looks like a square of lambda L minus d of lambda L b of lambda L, that is equal to 0. Okay. So if we substitute the terms which we found earlier, a, b, c, d, whatever, this equation turns out to be cos hyperbolic lambda L cos lambda L plus 1 is equal to 0. Okay. So those lambda values which will take this equation to 0 are indicative of the natural frequencies. Natural frequencies. And if you remember the lambda parameter, we had found lambda fourth was equal to omega square rho dash by EI. Okay. So now what? This has to be computed numerically. It's not a straightforward deal. Okay, this has to be computed using a software. So we have lambda 1L. If you do that, the first one comes out to be 1.875. The second one turns out to be equal to 4.694. Third one turns out to be lambda 3L is equal to 7.855 and so forth. Okay. And then what? We have lambda square is equal to omega times square root of rho dash by EI. Okay. So now if I write lambda square as lambda square L square, okay, by L square, then I get this omega square root of rho dash by EI. Okay. In other words, the omega, so this is, let me put an m over here. Omega m can be found by these values, lambda m L squared by L squared square root of EI by rho dash. Okay. Now the resonance frequency is found. Okay. So how do we find the mode shape? How do we find the mode shape? How do we find the mode shape? If you remember, our basic displacement was of this form: u3 of x is equal to u3 0 a lambda x. u3 0 is 0, so this term will not come. Then 1 over lambda du3 0 by dx at 0 into b of lambda x. This will also not come in because du3 dx is 0, but then I have 1 over lambda square d2 u3 by dx square at 0 c of lambda x plus 1 by lambda cube d3 u3 by dx cube 0 d of lambda x. Okay, so at a particular lambda, let's say lambda m, that means for a particular omega m, I can now find the mode shape. But the question is, what is d3 u3 dx square at 0 and also the third derivative? Okay, that has to be found from here now. Okay, that has to be found out from here, because at a particular lambda m or lambda ml, this is singular. Okay, so it will drop its rank by 1, and so these two equations are dependent. That means I cannot independently find double derivative at 0 and triple derivative at 0. I can only find a dependence. Okay, so now what happens? I have to find this quantity. I have to find this quantity. Okay, I have to find this quantity. So I will find this second quantity in terms of the first quantity. Okay, so how do we do that? We do that like this. My u3m of x is 1 by lambda m square d3 u3 m0 dx square, and I have c of lambda mx plus, okay, 1 by lambda m d3 u3 m by dx cube at 0 divided by d2, sorry, this is d2 u3 m by dx square 0 into d of lambda mx. Okay, I told you, because the two equations are now dependent, I cannot independently find second derivative at 0 and third derivative at 0. So now what we are doing is finding the ratio of the two, which can be done using the equations. So what is this? d3 u3m by dx cube at 0 divided by d2 u3m dx square at 0. Okay, you can see, okay, this divided by this, it's either this divided by this or this divided by this with a minus sign. So that's either equal to minus lambda m d lambda ml by a of lambda ml. Okay, so this is d lambda ml over a lambda ml, either that or it is equal to minus lambda m a of lambda ml by b of lambda ml into L, sorry, into L, into L. So the other possibility is a lambda ml by b lambda ml with a lambda in the middle and minus. Okay. So now if we use one of these definitions, any one of these definitions to plug it in here, we need this over here. Okay. So my u3 mx is equal to 1 over lambda m squared d2 u3m by dx square at 0 C of lambda mx, then minus, okay, using this definition, okay, because there is a lambda m on top and lambda in the denominator, you get a cancellation. So minus a lambda m l by b lambda m l d lambda m x. Okay, that's the mode shape. Okay, it's indeterminate up to this constant, otherwise the amplitude constant is not known, otherwise the shape is known. So the shape is known. Okay, so this is a clamped beam. Okay, so the clamped beam first mode looks like this, the second mode looks like this, and so forth, with slope 0, displacement 0. So up to an unknown constant we have determined the mode shape. Okay, later on when we normalize, that problem also will go away. Okay, so that is the mode shape and resonances of a clamped free beam. Clamped free beam. Okay, so we have the first system. At some point, maybe next class or so, I'll show you animations of the mode shapes. Okay, because that has to be done on MATLAB on a different monitor. I'll do it on another day. Okay, so next system is a simply supported beam. Simply supported beam. Simply supported beam. Now, because we have done one system, I will not repeat the whole process. So what are simple support conditions? So I have a simply supported beam. Okay, I have a simply supported beam. What are the conditions? The conditions are u3 at x equal to 0 is 0. So if this is x equal to 0 and x equal to L, okay, then u3 at x equal to L is also equal to 0. So it is 0 displacement here also. Okay, then mxx at x equal to 0 is 0. So the moment here is 0. So this cannot support a moment. This end cannot support a moment. Okay. Whereas at mx also, I mean x equal to L also, moment is 0. Okay. So now if we do the same to the form we found earlier, to this form we found earlier, this form, okay. If we use this form once again, what we will get is u3 at x equal to 0 should be 0. These conditions in terms of that u3 function, then u3 at x equal to L should be 0, then d2 big u3 dx square at x equal to 0 should be 0, and d2 u3 dx square at x equal to L should also be equal to 0. Okay. Now if we follow that procedure, okay, and come up with a matrix, and then the unknown conditions, we have du3 dx at 0 remains unknown, then the shear remains unknown, okay. Then for non-trivial values of this, the determinant of this matrix must go to 0. That determinant ends up as sine hyperbolic lambda L sine lambda L is equal to 0, and for lambda not equal to 0, this sine hyperbolic lambda will not be 0, which means sine lambda L must be equal to 0. Okay. Now if sine lambda L is equal to 0, that means lambda ML, multiple solutions are of this form, m is equal to 1, 2 and so forth. Okay. So then what? My omega m ends up as m square pi square by L square square root of EI by rho dash. Okay. These are my simply supported beam natural frequencies or resonance frequencies. Okay. And the mode shape as before ends up looking like u3m x is equal to, it looks very simple, 1 over lambda m d u3m dx at 0 sine lambda mx. Okay. Or we say a some amplitude or am sine m pi x by L. So we can plot or we can show these mode shapes. The first one for M1 looks like this, is a half cycle, half sinusoid. For m equal to 2 it looks like this, one full sinusoid. M equal to 3 it looks like this, 3 half cycles. So every m indicates one half cycle and so forth. Okay, so they look very simple. So I will close the lecture here. We have already looked at the natural frequencies and mode shapes of a beam, okay, under two boundary conditions. We will continue along these lines in the next class. Thank you.